Okay, let's unpack this. Imagine you're trying to build the absolute fastest race car. You optimize everything, right? Every nut, every bolt.
Maximum speed, that's the goal.
And then someone says, okay, great job. Now, to make it even faster, you need this special brake, like a super brake you can slam on any time.
Mm-hmm.
And when you hit it, the car limps along super slow for a bit. It just sounds completely backwards, doesn't it?
It absolutely does. But believe it or not, that kind of counterintuitive idea is actually central to a really powerful technique called deoptimization.
And that's used in, well, modern language runtimes. Specifically, we're talking about Ruby's JIT compiler, YJIT.
Exactly. YJIT, yet another just-in-time compiler. Its main job, fundamentally, is to swap out the standard Ruby interpreter instructions.
The virtual machine stuff.
Yeah, that stuff. And replace it with raw native machine code.
Yeah.
You know, the actual instructions your Intel or ARM chip understands directly.
And cutting out that middle interpretation layer, that's where the speed comes from.
That's the big win, yeah. And we're digging into this based on a really interesting recent talk about how YJIT works under the hood.
The performance gains aren't just theoretical either. We're seeing things like Rails bench running, roughly twice as fast compared to the interpreter.
That's right. And maybe even more relevant for folks out there in real-world production, like Shopify uses it heavily on their storefronts.
Right.
They've seen average speed-ups around 18%, sometimes peaking up to 33%. That's significant.
And it's not experimental anymore. It's production ready, fully baked in. It's actually the default in Rails 7.2 and up if you're running Ruby 3.3 or later.
So chances are, if you're reasonably up to date, you're already getting these benefits.
You might be racing along thanks to this deoptimization magic already.
Exactly. So our mission today in this deep dive is to really peel back the layers. We want to understand how YJIT gets these speeds, focusing right on this paradox, deoptimization.
Speeding up by knowing how to slow down.
Precisely. And yeah, the team's already working on the next thing, ZJIT, but this technique, deoptimization, it's absolutely fundamental to how we make dynamic languages like Ruby fast today.
Okay, so why should you, listening right now, care about this compiler stuff?
Well, because understanding deoptimization isn't just like a niche Ruby detail, it's a fantastic insight into the clever tricks language designers use.
Tricks to balance raw speed with the flexibility that makes dynamic languages so powerful in the first place.
Exactly that balance. It shows you the hidden complexity, the elegant solutions running underneath the code you might write every single day.
All right, let's dive in. What is deoptimization really? Why is having that emergency brake so critical for overall speed?
Yeah, how does hitting the brakes make the whole race faster?
It still feels weird.
It does.
Yeah.
But the simplest way to think about it is it's the ability to cancel an optimization at any time during execution.
Just undo it.
Yep. Throw it away. Now, why would you want to do that? The genius part is if you know you have a reliable way to bail out.
A safety net.
A safety net, exactly. Then you can be incredibly aggressive, really speculative, with the optimizations you try in the first place.
So you make a bold bet, optimize based on that bet, and if reality proves you wrong later,
you just hit the escape hatch, you de-optimize. And this is absolutely crucial for dynamic languages like Ruby.
Because Ruby lets you do things that would terrify a traditional compiler.
Totally. You can redefine constants whatever you want. You can change methods on just one specific object. You can hook into the execution flow in unexpected ways using things like tracepoint.
A static compiler would have to be super cautious, checking constantly.
Or just give up on optimizing much at all. But with deoptimization, YJIT can basically say, okay, I'm going to assume none of that crazy dynamic stuff happens most of the time.
Optimism.
Right. Compile super fast code based on that assumption. And if, on the rare occasion, someone redefines a constant or adds a singleton method,
then it gracefully falls back.
It uses deoptimization to switch back to the trusty, if slower, interpreter for that specific case, ensuring things are still correct.
And this isn't just an idea anymore. It's shipped.
Oh, yeah. The mechanism landed in Ruby 3.1, and it's been refined since. The idea was floating around earlier, sure, like at RubyKaigi 2016, but now it's actually in the Ruby you're running.
Making Ruby faster in the real world?
That's the goal.
Okay, let's get specific. How does YJIT actually use deoptimization? Let's talk about some of the techniques, maybe starting with the ones that were around before the latest Ruby 3.4, like code patching.
Right, code patching. This is a classic one. It deals with situations where YJIT thinks it knows the value of something, like a constant, and embeds that value directly into the compiled machine code.
Inlining the value.
Exactly. So say you have FU somewhere in your code. YJIT might compile a piece of code that uses FU, and instead of generating code to look up FU every time,
Which takes time.
right, it just sticks the value 1 right into the machine instructions. Or, technically, because of how Ruby tags integers internally, it might actually inline the value 3, which is how Ruby represents the integer 1.
Okay, so the fast machine code literally has the number 3 baked into it, assuming FU is always 1.
That's the bet. The
Yeah.
problem, as you know if you've worked with Ruby,
Constants aren't really constant.
bingo, you can redefine them. Later on, someone might write FU equals 5,000 trillion.
And YJIT's bet is suddenly very, very wrong.
Completely broken. So when that redefinition happens, the Ruby runtime notifies YJIT. YJIT then has to find all the places in its compiled code where it baked in that old value, that 3.
And fix it.
It patches it. It literally overwrites the machine instruction that had the 3 with a different instruction, a jump.
A jump. To where? Does it jump to code that looks up the new value?
Not directly. It jumps to a special piece of code called a trampoline.
A trampoline.
Yeah, think of it like a little redirection service. Its only job is to transfer control back to the Ruby interpreter.
Ah, okay. So it doesn't try to fix the optimized code. It just bails out of it.
Exactly. The next time the program hits that patched spot, instead of using the old wrong value 3, it hits the jump, goes to the trampoline, and execution continues in the interpreter. The interpreter, being slower but more careful, will correctly look up the current value of FU, the 5,000 trillion, and carry on.
So that specific optimization, the inlining of that constant, is just canceled for that location.
Yeah.
Very targeted.
It's surgical. But sometimes the dynamic changes are so profound, so widespread, that patching individual spots isn't enough.
Like you need to throw away bigger chunks of optimized code. Global invalidation.
Precisely. And the classic example highlighted in the sources is using tracepoint.line.
Right. Tracepoint lets you set up hooks for various events, like running some code every time a specific line is about to execute.
And that's the killer part. A tracepoint.line hook can run any arbitrary Ruby code right before that line. The example given is wild. You could have a method that looks like it should just return 1.
Yeah, seems simple enough.
That. A line tracepoint is active. And just before the return 1 line, the tracepoint's code fires, reaches into the caller's scope, finds a local variable there, and sets it to 5,000 trillion.
Wait, the tracepoint can modify variables in the caller?
Yeah. It's incredibly powerful, maybe dangerously so, for optimization. So because a line trace can potentially mess with anything local variables, global state, call stack YJIT just can't make reliable assumptions across line boundaries when one is active.
So if I enable tracepoint.line, what's YJIT's reaction? Does it just give up?
Pretty much, for the affected code, it performs a massive de-optimization. The talk mentioned YJIT generating literally thousands of jump instructions.
Thousands?
Yeah. It scatters these jumps throughout the compiled code. They act like emergency exits, forcing execution back to the interpreter whenever the code hits a point that might be influenced by a line trace.
Wow. So turning on line tracing basically disables YJIT for large parts of your code.
It significantly degrades its effectiveness, yes. It neuters the JIT.
Which leads directly to some very practical advice that came out of this. Let me guess.
Don't use line trace point in production, unless you absolutely have to, for some critical debugging. Understanding how it fundamentally breaks JIT assumptions makes it obvious why. It's a debugging tool, not a runtime feature you want active normally.
Makes total sense. Okay, so that's some of the older stuff. Let's shift to Ruby 3.4. It sounds like they added even more sophisticated de-optimizations.
They did. They tackled some really tricky edge cases that were limiting YJIT's ability to optimize further or causing potential correctness issues. One big one is handling escape locals.
Escape locals, like local variables escaping their method.
Exactly. Normally you think of local variables as private to a method, but in Ruby there are ways, especially through the C API or using the binding object, for a code to actually peek into or even modify local variables in the method that called it.
Whoa. So even if I don't pass a variable x to a method foo might be able to find my x and change it using binding.
Potentially, yes. It breaks the simple model. Now, before Ruby 3.4, YJIT tended to store local variables in memory on the stack. This was slower, but made them accessible if something needed to escape and find them.
Okay.
In 3.4, YJIT got more aggressive. It started storing locals in CPU registers whenever possible. Registers are way faster, they're right there on the chip.
Like a traditional compiler would do. Much faster access.
Much faster, but registers aren't as easily visible or modifiable from outside the currently executing compiled clone, so the optimization is keep locals in fast registers.
And the deoptimization.
It's triggered when something potentially accesses the caller's frame, like fetching a binding. That signal is a possible attempt to mess with locals that YJIT thought were safely tucked away in registers.
So YJIT sees the binding call and gets nervous.
Basically, yeah. It realizes its assumption about register safety might be violated, so it deoptimizes. It throws away the compiled code for that method and sends execution back to the interpreter. The interpreter manages locals on the stack where they're accessible via binding, ensuring correctness.
Optimize for the fast, common case, no binding, and bail out if the dynamic escape hatch gets used. Very clever. What else is new in 3.4?
Handling singleton classes. This is another classic Ruby dynamic feature.
Right, where you define a method not on the class, but on one specific object instance.
Yeah.
Like misstring.define_singleton_method.upcase.
Exactly. So only that one string object, misstring, now has an upcase method that returns foo, while all other strings behave normally.
How does that trip up YJIT?
Well, imagine YJIT sees a call like misstring plus bar. It checks the type, sees it's a string, and probably compiles highly optimized code assuming the standard string plus method for a concatenation.
Makes sense.
But what if later in the program someone defines a singleton plus method specifically on misstring? Maybe misstring.define_singleton method plus other bazmazels.
YJIT's compiled code is now wrong. It expects concatenation but should be calling the singleton method.
Precisely. If YJIT just runs its optimized concatenation code, it might produce misstring bar, when the correct result, according to the new singleton method, should be bez. That's a miscompilation, a wrong answer.
That's bad. How does 3.4 stop that?
YJIT in 3.4 got smarter about this. It now specifically tracks when singleton classes are created for objects of common, heavily optimized types string, array, hash.
It watches for them.
Yeah. If it sees a singleton class get created for, say, a string object, it invalidates any compiled code that might have made assumptions about string methods for that specific object, or potentially for strings in general in certain contexts. It might also start skipping certain aggressive type checks it previously performed.
So it de-optimizes proactively when it sees a singleton might be involved.
Essentially, yes. It makes sure that if a singleton method could exist, it falls back to a safer path that actually looks up the method at runtime, rather than assuming the standard one. Correctness first.
That sounds like a really important fix for correctness.
Yeah.
But what about exceptions? Debugging can get weird with optimizations like inlining.
Oh yeah, that leads to the next big 3.4 improvement, lazy frame push. This tackles a problem with method inlining.
Inlining is when YJIT copies the code of a called method directly into the caller, right? Avoids the overhead of a separate call.
Exactly. It's a huge performance win. But to make it even faster, YJIT often skips creating a standard method frame on the call stack for that inlined method. A frame is like a bookmark, recording which method is running, where it was called from, etc.
And why is skipping the frame a problem?
Backtraces. When an exception happens, Ruby walks up the stack looking at those frames to build the backtrace that tells you how you got to the error.
So if there's no frame for the inlined method.
It just disappears from the backtrace. You get incorrect or incomplete debugging info. The source used an example like calling string.setByte 0a on an empty string. That should raise an error, and the backtrace should clearly show that the error happened inside setByte.
But without the frame, setByte wouldn't be listed, making it harder to debug.
Exactly. The optimization breaks the observability. So Ruby 3.4 introduced lazy frame push. Yeah, here's how it works. If YJIT is running inline code, and it hits a situation that would cause an exception, like the invalid index in setByte, the very first step is usually allocating the exception object itself.
Oh.
That allocation process now triggers a special hook inside YJIT. This hook looks at the current location in the program counter. It checks if this location corresponds to a point where a method was inlined and a frame was skipped.
So it knows, we're crashing inside an inlined method.
Right. And if it determines that's the case, it doesn't just raise the exception immediately. It first lazily pushes the missing method frame onto the stack right then and there, just before the exception propagates.
Well, It reconstructs the missing frame just in time. How?
It uses information YJIT stored earlier when it did the inlining, information associated with that specific program counter location. Things like where the original method entry point was, where the receiver object is stored. It pieces the frame together on the fly.
That sounds incredibly complex.
It is, and the talk acknowledged it's not perfect. Because of polymorphism, the same piece of compiled code might handle calls to different methods depending on the object type. Mapping a program counter back to the correct method entry isn't always simple. Sometimes it might still have to de-optimize fully and go back to the interpreter to guarantee a 100% accurate backtrace.
But the goal is to provide correct backtraces more often, even with aggressive inlining.
Exactly. Improving debuggability without sacrificing too much performance.
Okay, one last related thing mentioned was about YJIT only do methods and something called ctrace. This isn't strictly de-optimization, is it?
Not exactly de-optimization itself, but it's tightly related to managing behavior based on whether YJIT is compiling or not. It stems from efforts to rewrite some core Ruby methods in Ruby.
Wait, rewriting methods like array hash each, which are usually written in C, in pure Ruby.
What? Performance? Potentially. The idea is, if array hash each is written in Ruby, YJIT could inline it and compile it right alongside your application code. This avoids the overhead of jumping between YJIT compiled code and the C implementation in the Ruby runtime.
Less boundary crossing.
Right. They actually tried rewriting array hash each in Ruby, found it was faster in microbenchmarks, but actually slower in larger applications, maybe partly due to complexities or the boundary cost not being the only factor.
So what's the 3.4 approach?
A conditional swap. There's now helper check. If the standard C implementation of a method like array hash each hasn't been redefined by user code.
So it's still the original C version?
Yes. Then, only when YJIT is enabled, the runtime can undefine the C version and define a special Ruby version instead. So YJIT gets to work with the Ruby version, aiming for better optimization potential.
Clever. But you mentioned a problem with backtraces.
Yes, a subtle but important compatibility issue. Methods implemented in C often appear differently in backtraces than methods implemented in Ruby. A C method might just show as EE or something internal, while a Ruby method shows its final name.
Okay.
If YJIT sometimes uses the C version and sometimes swaps in a Ruby version, the format of your backtraces could change depending on whether YJIT is enabled or active.
And that could break things, like tests.
Exactly. Many test suites unfortunately rely on matching specific lines or formats in exception backtraces. Suddenly changing how array check each appears could cause perfectly good tests to fail just because YJIT was turned on.
Ouch. That's a nasty side effect of an internal optimization.
It is. So the solution is the ctrace attribute. It's an internal flag set using a special syntax like primitive attery. When this attribute is applied to a Ruby-implemented core method, like the YJIT preferred array check each, it tells the backtrace mechanism, hey, even though this is Ruby code, make it look like a C method in the backtrace.
So it fakes the appearance for consistency.
Pretty much. It preserves the expected backtrace format, ensuring backward compatibility and preventing tests from breaking randomly just because YJIT is doing its job optimizing internals. It's about managing the observable behavior, even while changing the underlying implementation.
Okay, wow. That's a lot of intricate mechanisms. So, pulling it all back together, de-optimization isn't really about slowing down, is it?
Not in the end goal, no. It's the opposite. It's the crucial safety valve that allows YJIT to be incredibly aggressive and optimistic in its optimizations.
Because it knows it can always hit the brakes if its assumptions turn out wrong.
Precisely. It can speculate that constants won't change, that methods won't be redefined on the fly, that locals won't escape, and if those dynamic Ruby features do kick in,
De-optimization handles it, invalidating code or jumping back to the interpreter to ensure correctness.
correctness is paramount. And Ruby 3.4 really leveled up this capability, adding these sophisticated deops for tricky cases like escaped locals, singleton methods, and getting exception backtraces right even with inlining.
All contributing to making YJIT faster and more robust in the face of Ruby's inherent dynamism.
Absolutely. The whole story really highlights this fundamental tension, doesn't it, in dynamic languages?
The push and pull between performance and flexibility.
Yeah. How do you get maximum speed? Which often relies on making assumptions and compiling static code, while still fully respecting the language's promise that, well, almost anything can change at runtime.
It's a constant balancing act.
It really is. And YJIT's journey, especially its deep reliance on de-optimization, is just a fascinating case study. It shows how sometimes the smartest way to go faster overall involves building in a really intelligent way to strategically slow down when you have to.
Mhm.
Makes you think, doesn't it, about all the complexity hidden just beneath the surface of the languages we use every day.